Hello everybody, welcome to my talk. My name is Bonaventura del Monte. Today we are going to talk about enabling reliable and continuous stream processing when stateful operators hold terabytes of state, even in the presence of failures and data rate fluctuations. Imagine we are managing a large real-time bidding platform. On one hand, we have a large use base with up to 100 millions of users, for instance, that generate millions of events per second, and we can have in flight in the platform up to 1 billion of events. This results in a high cardinal data stream that a scale-out stream processing engine has to cope with. On our scale-out SPE, we want to deploy multiple long-running queries that contain large temporal aggregation and joins. The output of these queries are used in other critical real-time subsystems, such as we might have a real-time dashboard connected to the SPE. Overall, this setup leads to very large distributed state for operators that the SPE must manage while guaranteeing exactly once processing semantics, meaning that each operator must be processed only once. And we also want to ensure that the SPE delivers robust query performance. However, things can go wrong, and we might have anomalous operational events in the system, such as we could have fluctuations on the data rate of the input streams, and we could also have failures in the SPE itself. As a result of these events, an SPE has to reconfigure itself. For instance, it has to redeploy a query to increase the parallelism of the query just to cope with an increasing in the data rate of the input stream. However, this can lead to an increase in latency, downtime, and also might also incur into data loss. In short, it can be a disaster. Based on this observation, we looked at how well the current generation of SPEs can cope with those situations. Specifically, we looked at production-ready systems such as Apache Spark and Flink, and research prototypes such as SIP, Chi, and Megaphone. On one hand, production-ready systems allow for reconfiguration of a query upon a restart, so they use stop-the-word approach, but they support state in the sizes of terabytes. On the other hand, research prototypes can handle fine-grained configuration of a running query, but they are not designed to support large operator state efficiently. Ideally, what we want is to have the best of both worlds. So what we did was to take a closer look at two of the before mentioned systems, and so we chose Apache Flink as representative of production-ready SPEs and Megaphone as representative of research prototypes, as this was the latest to be proposed in the last year VLDB. We then deployed these two systems on a cluster of 8 servers and executed a query number 8 of the NextMark benchmark, which is one common benchmark for SPEs. And it actually simulates a bidding platform, so it's pretty close to our use case. Query 8 consists of a window join of many hours that can lead to large operator state. What we did was to execute this query until it will reach a certain amount of state, and then we triggered a migration of all the physical operator instances running on one VM to a 9th pre-provisioned VM, and we measured how long this process will take. What we found out is that the query restart of Flink requires time proportional to the transfer of the state between the two VMs and that are part of the migration. In contrast, what we saw in what we could observe in Megaphone is that this process is indeed faster because Megaphone is designed for fine-grained migration. However, it cannot complete migration that involve a state transfer when state is larger than half a terabyte. So, driven by these findings, the research goal of this paper is to provide efficient ways of managing large operator state and reconfiguring running queries on the fly, even when we have operator state in the sizes of terabytes. And so we want to do so just not for the sake of providing those techniques, but because we want to enable features like fault tolerance, resource elasticity, and runtime optimization, such as load balancing. We identified 3 research challenges that prevent current generation of SPEs to provide efficient state migration and on-the-fly reconfiguration of running queries when state is large. These are the processing overhead that the reconfiguration and state migration will occur. So we really want to have something that will have minimal impact on the query processing performance. We ideally don't want to break exactly one's processing semantics. So there is a challenge that consists in delivering consistent results. And finally, the state migration per se must not introduce network overhead. Our solution is Rhino. Rhino is a library for efficient remanagement of large distributed operator state. What we did was to devise with Rhino a protocol that would enable reconfiguring only a subset of the physical instances of a running query, assuming that their state is periodically checkpointed to a distributed file system. This reconfiguration is consistent, so it doesn't break exactly one's semantics requirements, and it does the reconfiguration without altering the query execution. So I'm not going to go into the details of the protocol, but I really do invite you to read our papers where you can find more details. What we could achieve with this Handover protocol was a reduction in the reconfiguration time of a factor of at least 4 compared to baseline. And this happens just because we rely on the checkpointed state on a distributed file system that can be recovered only by the instances of an operator that we want to reconfigure. However, we still were not convinced of our results, and we tried to understand what's the bottleneck in the current when using this Handover protocol. What we found out was that relying on a distributed file system means that we cannot control where this will store files that contain the checkpointed state that will be used when a new instance takes over. Please take into account that for stateful operators, they cannot be resumed easily without having the state of the computation, because they cannot produce output by only having an input record. They also need the current state. So what happens is that if the newly spawned instance doesn't have its state, it has to fetch it via the network from the distributed file system, and this might be slow. What we want to have is that the state for a task, so for an instance to be resumed, has to be already local to the virtual machine where we restart this in operator instance. So what we did was to devise a state migration protocol that proactively and incrementally migrates state to serve future reconfiguration. And our protocol is designed to support large state sizes. I'm not gonna go through the details of this technique, but I really do invite you to read the paper to get more details about it. So using our protocol, our two protocols, so the Handover and the state migration protocols, we were able to further reduce the reconfiguration time by up to a factor of 15 compared to baseline solutions. So we show that reconfiguring a query with large operator state is feasible and also doesn't impact the performance. So in this paper and in the Rhino paper, we make the following contributions. We enable on-the-fly reconfiguration of running queries with large stateful operators. We support fault tolerance, resource elasticity, and runtime optimization, such as load balancing for running queries with large stateful operators, and we validate our system design at terabyte scale. To validate our system design, what we did was we selected as main metric the end-to-end processing latency, which is the difference in time between the moment a record goes out of the SPE and its generation timestamp. To this end, we have an event time data generators that write data into a reliable queue that we use for upstream backup. And from this queue, we have the SUTs, which in our case are Fling, Megaphone, and Rhino, that will read from the queue. We execute the next benchmark suite on a cluster of 16 virtual machines. In the remainder of this talk, we will focus only on the query 8 of this benchmark suite. So we have many experiments in the paper, but one that I want to show you today is this one. Here we have three scenarios. We have load balancing on the left, we have scaling out in the center, and we have a recovery on the right. What we did was to, in each of these three scenarios, we let each SUT to run until hundreds of gigabytes of state are stored in memory, and then we triggered one of these the three events. Then we wait until each SUT gets back to normal processing. We also push our SUT to process real-time data at a common sustainable rate, which results in a constant end-to-end latency. In the first experiments, we also include megaphone that allows for load balancing. What we observe in all the plots is that after we trigger one reconfiguration, baseline systems exhibits a latency increment, whereas Rhino does not. Overall, Rhino keeps latency in check in all the three settings, whereas other SPEs have an increment in latency up to 3 orders of magnitudes. So in conclusion, with Rhino, we are able to remove the bottleneck due to large state transfer upon a reconfiguration of our running query. We enable fault tolerance, resource elasticity, and runtime optimization, such as load balancing for running stateful queries. And we validate our system design at terabyte scale, and we show that we are able to reduce up to 3 orders of the latency upon a reconfiguration up to 3 orders of magnitude. And with this, my talk is over. I thank you for your time. I just want to say that I will be on the job market starting from next winter, and now I'm looking forward to your questions.